Hello everyone, my name is Adam. I'm a junior developer at Cesnet and a student at Masaryk University here in Czech Republic, in Brno. Sadly, Eliška couldn't join me today, so I will try to present her part of the presentation or summarize it. So I'll be talking about how we try to accelerate Suricata with the RTE flow rules. And to give some background about RTE flow rules and how we did it. So on my agenda, I will be talking about what is Suricata in general. Lucas gave us a nice overview, so I will try to just summarize it. Then I will be talking about RTE flow rules, so we are all on the same page. I will be talking about how we needed to rework the RSS that was already in Suricata to support our acceleration. And then I will be talking about the specific accelerations we did in Suricata. Those are the static drop filter and the dynamic bypass. So about Suricata, it's an open source network detection engine developed under OISF. It can act as an intrusion detection system or intrusion prevention system. It's based on, it matches traffic based on signatures. As you can see, here is an example of signature like this. It consists of 3 parts. Here is the action part that basically tells the Suricata what to do. Here is the header. It consists of the protocol, of the IP addresses and the port, and also it states the direction of the flow. And then there's the rule options or the signature options part, which can contain a variety of keywords which we utilize in the bypass. One specific one, I will get to it later. Also, Suricata supports multiple packet acquisition modes. For example, AF packet, PF ring, or the most important for us, DPDK. So Suricata, as an intrusion detection system, lies behind the firewall in the network. It can issue signature-based alerts. It can export flow information. Also, it can extract files, certificates, keys, or record PCAPs for later analysis. What was our motivation behind accelerating Suricata? As Suricata can work in a high-speed environments, there can be peak moments in the traffic where not all traffic is analyzed, and during these peak times there can be flows that are unwanted and we know they are safe, so we can not analyze them basically and offload this dropping or this filtering into the NIC, into the network interface card. As I mentioned, we implemented it with the drop filter, the static filter, and the dynamic bypass. And our goal was to stay as generic as possible to the hardware we support. So those are NICs with MLX5, ICE, I40E, and IXGB PMDs. And we are also supporting this feature across different DPDK versions, supporting from version 19. Okay, so how we did the acceleration. I will give some background on the RTE flow rules at the start. RTE flow rules are generic rules offloaded to NIC with the help of the DPDK API. So the DPDK application calls on some DPDK function, RTE flow create. The function creates the rule inside of the NIC with some parameters that I will get to in a minute. And then the rule acts there independently of the application. So as a structure of the RTE flow rule, it contains attributes, which basically define how the rule works, or how the rule acts. There can be, for example, ingress egress, meaning if it's supposed to match incoming or outgoing traffic. Priority group, those are helpful when trying to organize or making some hierarchy of different rules. Yep. There's the matching pattern part, which specifies what flows to match. You can specify different protocols, also some of their specification. For example, you can see we can specify some IP address or yes, and actions. There is the actions part. We can utilize different actions. For example, RSS, drop, count. There's many more. Those are the main ones we are utilizing. So about how we needed to rework the RSS. Before it was initialized by the structure mentioned here. But we lacked the ability with this approach to chain the rules together or make some hierarchy with RSS. So we wanted to avoid the situation that, for example, the packets would be dropped or wouldn't be dropped because first they were redistributed with RSS. So we need to rework the RSS into the RTE flow API. Yes, we ran into some issues. It was a quite complicated task because not all the time I could find specific examples how other application utilize it on the specific NICs. So yeah, and when we were implementing it for 4 NICs, it took some time to figure out all the specifics of it. And also we were implementing it throughout different versions of DPDK, so that was also a drawback on the time. Some of the functions we ran into, for example, hash functions hash function support of the RSS were different across versions. We needed to catch this. For example, MLX5 support or needs just one generic rule for all the traffic that comes into the NIC and can redistribute the traffic just thanks to this one rule. But for example, for the ICE PMD, there is one rule for the IPv4 traffic, one rule for the IPv6 traffic, and the L4 protocol doesn't matter. But for the I4TE, there is separate rule for each IPv4 combination with each L4 protocol and different rule for each IPv6 combination with all the L4 protocols we support. So yeah, that was about the RSS stuff we did. And now to the main part, to acceleration or the offload we did with the drop filter. So the drop filter is a BPF-like filter built on RTE flow rules. The rules are loaded to the NIC before the start of Suricata. They are predefined in the configuration file of Suricata. I will show you an example in a minute. And the goal was to reduce the load on Suricata so it doesn't have to analyze all the unwanted flows. As you can see, the example, it's quite simple. The NIC has some rule with a specific IP address. In this example, there are incoming flows. The flows are not matched, so Suricata analyzes them. The flow is matched. Suricata doesn't analyze it. And what flows can we leave out of the inspection or the analysis? Usually, those are verified or safe flows. Or flows with, there can be flows with forbidden inspection, that by some authority it was forbidden to inspect them. And some of the flows, like we know there are verified or safe flows, are some streaming services or when we have a private server with data backups. yeah, we don't need to inspect that, so we can leave Suricata to do more important work. How does the Suricata operator define the rules? We were inspired by the test PMD syntax, the DPDK test PMD application. Sure know. But we just took out the pattern part. There is an example here. Just this is the full string that would be in the configuration file for matching one specific source and destination or flow with these parameters. As we do not support full BPF capabilities, we were not thinking about or we didn't approve of the BPF syntax, but there are still ideas, and we are still a little bit brainstorming about how we could improve the syntax. So if you have any ideas, feel free to let me know after, and I will be grateful. So yeah, here is a example of a configuration file of Suricata. This is the DPDK part. Here is the PCI address of the NIC we are working with. There are some DPDK parameters, and there is the drop filter. In this example, I have 4 rules. One for matching this specific source IP address, or flow with this specific IPv4 address. Rule with one specific source and destination. There is a range of IP addresses here, and just all the flows that match these protocols. Okay. Also, to measure the performance and verify the functionality of the filter, we wanted to implement some counters that we could extract the number of filtered packets from the flows. We did this with the help of the count action, the RT flow count action. But sadly, it was not supported on I40E, so it supports the I40E supports the drop filter, but we cannot extract the statistics from it. But on the MLX5 and ICE, this functionality is supported. Yeah, but we had one drawback with the ICE, or I can say 2 drawbacks with the ICE PMD, with the count action. Because of the internal working of the ICE PMD, we cannot use masks in the pattern. So each rule has to be one specific flow, and this also reduces the amount of flows we can filter this way. So yes. Here there is a simplified version of a sequence diagram of the process, how rules are loaded and the statistics are extracted. So Suricata is launched, then in the process setup, setup process, the RT flow create is called, all the rules are created in the NIC, and then when Suricata enters the receive loop, and the periodic counter check comes, you can see here that we query each rule and get the statistics of each rule. We accumulate it, and then we update the global Suricata statistics with this. Also, the counters were very useful while developing Suricata CI. It's our test framework for measuring Suricata performance. It's based on PyTests, and we generate the traffic with tracks, traffic generator, and the Suricata receives the traffic. The topology, you can see here, we have a tracks in loopback mode and the switch, and one port of the switch is mirrored to Suricata to receive all the eggs and takes traffic. We did some performance tests on this. They are still in development, but like the early tests showed that on HTTP, HTTPS, and SMB traffic, Traffic profile for tracks. When we filtered half of the traffic, we doubled the performance of Suricata. So when we filtered the unwanted flows, it clearly showed that the performance of Suricata was increased. Yes, now about the dynamic bypass, the dynamic filter based on RT flow rules. As I mentioned, the Suricata signatures, or sometimes called rules, can contain in the options part a keyword bypass. This means that the flow is not to be inspected anymore when it's active. Again, usually these flows are some large expected flows from YouTube, Spotify, Netflix, or some encrypted flows, or the flows which an inspected stream depth was reached, meaning that they shouldn't be inspected anymore. And the goal again of this was reduce load on Suricata by offloading to hardware. Until now, Suricata was doing this bypass in the software, so this was more load on the CPU that we could potentially offload to NIC, to the hardware. Initial idea was to utilize the drop and age actions. Age action basically we can set a specific timeout interval that after that timeout the rule will generate some alert, or we can extract from the rule that okay, the flow has timeouted, the flow that was matched against this rule, but it was only supported on MLX5 from our hardware, so we didn't think this was general enough. We were looking for another solution, and currently, as the dynamic bypass is still work in progress, we are using drop and count actions. Both are supported on MLX5 and ICE, and we are also utilizing a special thread we call a bypass manager to not put more load on the workers, so the bypass manager can manage this, offload these rules and everything around it. And I didn't mention until now that when a flow becomes inactive after some timeout, the corresponding rule, the RT flow rule, is destroyed, so it doesn't take space in the NIC. More about the Suricata threading model we have. There are workers that pull and analyze packets, pull it from the NIC and then analyze them. We have a flow manager that manages the flow table and the state of the flows. And also we have, as I mentioned, the bypass manager that manages the bypass of flows. Here on this diagram you can see how each of these components communicate with each other. The workers pull from the NIC, from the queues. We utilize RT ring to send the information about these flows to bypass manager. Also, the workers communicate with a global flow table that keeps the states of the flows. The bypass manager also communicates with the internal flow handler table that we were implementing, that basically keeps information about the flows and their corresponding RTE flow rule handlers that are like the opaque handlers that correspond to the rules, and then based on that they can be destroyed, or the rules can be destroyed or queried. And yes, also there is the flow manager that manages the components of the flow table. Sorry. And here you can see the first part that happens in the dynamic bypass. That's the applying or loading the RTE flow rule. When the packets comes to the worker and the flow that is bound to this packet is supposed to be bypassed, the flow is added to the flow table. Then the flow passes, or the worker passes the attributes of this flow to the bypass manager. We utilize also RT mempool and RT ring. The bypass manager then dequeues the needed information about the flow, creates RT flow rule, in the NIC. If the rule was created successfully, we then set the flow of the state of the flow to capture bypassed. That means that Suricata doesn't have to worry anymore about the state of the flow because it's bypassed, and we add a entry to the local flow handler table. In the case that the loading is not, or the creation is not successful, maybe because the maximum number of RT flow rules was reached or some other error happened, we just set the flow back to local bypassed, and we let the Suricata handle the bypass. Okay, and the other part of the dynamic bypass is checking the flows and destroying them, and destroying the rules, the corresponding rules. So there is a periodic check of all the bypassed flows, and we for all the flows query the NIC for the filtered packet count, and then you analyze this information in the bypass manager. Then the bypass manager decides, okay, if the packet count was 0, so the flow was inactive, we destroy the rule, so it doesn't take space in the card. We set the flow state to local bypass, so Suricata can handle the bypass by itself, or then delete the flow from the table, or do the appropriate actions. And yes, then we remove the entry from the flow handler table and repeat this for every bypass flow. Okay, that was everything from me. Thank you for attention, and if you have any questions, you can ask now. Yes?
So when you're offloading the rule, sometimes it's possible to get another packet in between, right?
Yeah.
So I'm guessing that you keep some kind of information that you offloaded the rule and you don't need to track it again, or even if you got this packet, right, inside the Suricata.
Like you mean situation when another packet from the same flow?
Yeah, it's possible that you'll get 2 packets from the same flow.
Yeah. We do it. That's basically the Suricata part that was already there with the worker when it marks the flow as captured, or it's marked as bypassed. Then all the from my understanding, I was not implementing this. It was already in Suricata. All the packets are then from the same flow are bypassed. Like yeah, only the first packet is offloaded, or like it goes to the bypass manager, and the bypass manager works only with the first packet from the flow.
And one more question: the bypass manager basically it's a different thread, right?
Yes. It's
maybe
different.
I missed something. Okay.
Yeah, sorry, maybe I didn't mention. Yeah, all of these are different threads, and there's the NIC. Okay, thank you. Yes.
You mentioned running into these issues with different rules being needed for different network cards.
Yeah.
Did you just resolve that by coming up by basically treating the different network cards differently and coming up with certain rules that work for certain network cards, and that's basically the way you handle it?
Yeah. Like we need to figure the combinations, for example, with the RSS, with the right hash functions, or with the right setting up the queues for the receive queues with a different, for example, with a different RT flow rule. Then it sets up the pattern, or like there was many combinations of that we needed to implement. Yeah, but we tried like the core to be the same. Also with the drop filter, we tried to do the filtering part and the statistics part to be independent, or like not to be dependent on it. So like the I40E still can work with the drop filter, but doesn't count the statistics. Or if I answered your question.
You did. Thank you very much.
Thank you.
Yeah, thank you for showing the limitation you found in the DPDK flow implementation. For sure, there are many limitations depending on drivers, etc. That's probably something we should improve. And the first step to improve that is documentation, for sure. Some work is in progress to improve documentation of the Flow API in implementations. Second step is what you did, I think. You are doing some tests.
Okay.
That's very good. You show the limitation. Maybe you can go a bit further by creating some bug entries. I mean, some limitation cannot be changed if it's not supported in the hardware. Maybe there is no way to implement it.
Yeah.
But sometimes we can do something like you mentioned. You need two rules for IPv4 and IPv6. Maybe in the driver we can manage that. So I think we could open some bug entries for such limitation and try to remove these limitations.
Okay.
Yeah. Then the next step is to automate the test. This is what is done currently in the DTS group. So if you're interested, you can join the development of DTS. For remaining, DTS means DPDK Test Suite, and Flow API is starting to be implemented, right, Patrick? Yeah. Yes, that's correct, and you'll talk about it. So yes, for sure, we want to automate testing of the flow implementations, and we will be able to find more limitations. And then maybe a future step could be to have a kind of validation of drivers, show which drivers are following some global common behavior or not, and maybe it's a good incentive for driver developers to remove some limitations. What do you think about it?
I probably didn't catch the meaning of the question. I was listening.
I mean, okay. First question is: do you think it's very important for DPDK to remove the limitation we have in some driver implementation regarding the Flow API? Or can you live with these limitations, or do we think we should really work on it?
Like some depends probably on the hardware we are supporting. So because on some it was actually okay, we didn't run onto almost any limitations, but yeah, maybe just I will maybe just sideway a little bit. A few years back, there was also one group from our company that did a project called RT Flow Checker, and I really liked the idea behind it. It was basically just testing the capabilities of different NICs for RT flow rules, but it's not. I think it's not supported for the new versions of DPDK, and that seemed like a good way to check what is possible. So maybe when not supporting, I don't know, the more capabilities on the hardware or in the DPDK community, as you said, then some checking tool like this to be officially supported, that seems like a nice idea to me.
Yeah, I think the way to have it officially supported is to integrate with DTS. Really.
Okay. I hope I answered your question.
Yeah. I want you to say, yes, it's a big problem, we need to work on it. Just say that.
Okay. Yes, it's a big problem, we need to work on it.
Okay, we'll work on it.
Okay, thank you.
Thank you.